All right, today we're jumping into the tiny, tiny world of biology to talk about something absolutely essential, enzymes. You know, they're kind of the unsung heroes working inside you, like right now, making everything, well, work. So how do they do it? Let's find out.
So, get this. Every single chemical reaction that builds you, that keeps you going, is ridiculously, impossibly slow. I mean, so slow that life itself shouldn't even be possible. So, how are you alive? What's the big secret?
Yeah, without some kind of biological kick in the pants, life would just be stuck in this massive traffic jam. Seriously, the chemistry would grind to a complete halt. But, nature's pretty smart. It's got a trick up its sleeve.
And here it is. This is the solution. Meet the enzyme. So what is it? Put simply, an enzyme is a protein catalyst. Its whole job is to find a specific chemical reaction and just speed it up. And I mean way faster. The best part? It doesn't get used up in the process. They're basically the ultimate efficiency experts of your body.
And that's what makes them so brilliant, right? They're total specialists. They're reusable, you only need a tiny amount of them, and they are laser-focused on one single job. They don't change the final result, they just get you there a whole lot faster. It's efficiency on a molecular level.
So, how do they actually pull this off? Well, let's take a look at the mechanism. You can think of it like a very specific, very secret handshake happening between two molecules.
Okay, so it all starts here. First, you've got your enzyme, we'll just call it E, and then you have the molecule it's designed to work on. That's called the substrate, or S. Right now, they're just kind of floating around in the cell, waiting to bump into each other. And then, they meet. The substrate docks into this really special pocket on the enzyme called the active site. This is the handshake moment. Once they bind together, they form what's known as an enzyme-substrate complex. And this is where all the magic happens. So inside that complex, the enzyme gets to work. It transforms the substrate into a brand new molecule. That's the product, or P. And as soon as the job is done, it just lets go. The product floats away, and check this out. The enzyme is totally unchanged, ready to go again. It can do this millions of times a minute. It's incredible.
And this cleft, or pocket they talk about, that is the key to everything. It's not just some random shape. This 3D space creates this perfect little microenvironment with exactly the right chemical properties to get that specific job done.
So for a while, scientists thought this fit was like a simple lock and key, you know? The substrate had to be a perfect match right from the start. But it turns out it's way more dynamic than that. The more modern idea is the induced fit model. This shows that the active site is actually pretty flexible. As the substrate gets closer, the enzyme literally adjusts its shape to create an even better, more perfect grip. It's less like a rigid key and more like a firm, customized handshake. And this specificity is just everything. It is not a one-size-fits-all kind of deal. Your body has this massive, highly specialized army of enzymes, with a different one for pretty much every single chemical reaction that needs to happen. In fact, even though there are thousands and thousands of different enzymes, biochemists have been able to group them all into just 6 major classes, 6 main jobs.
And here they are. You've got your oxidoreductases that manage electron transfers. Transferases move chunks of molecules around. Hydrolases act like molecular scissors that use water to cut things. Lyases are also scissors, but they don't use water. Isomerases just rearrange the atoms within a molecule, and ligases are the glue. They join 2 molecules together. A specific tool for every single job you can imagine.
And this is the big takeaway. This incredible specificity is how a cell controls its entire metabolism, all the pathways that make up life. It's all about controlling which enzymes are on and which are off at any given moment. They are the ultimate project managers inside every cell.
But having all these super powerful accelerators running around would be total chaos without a way to control them. So how does a cell manage all this? Well, it uses a whole series of on and off switches. So how does a cell keep these powerful little machines in check? It basically has 3 main levers it can pull. It can tweak the environment, things like temperature and pH. It can add or take away helper molecules called cofactors, or it can use specific blocker molecules called inhibitors to just shut them down. Let's take pH, for example. Every single enzyme has a sweet spot, an optimal pH where it works at its absolute best. But if you move too far in either direction, if it gets too acidic or too alkaline, the enzyme shape starts to warp and its activity just tanks. This is a super simple but really effective way the body regulates reactions in different places, like your stomach versus, say, your intestines. But for more fine-tuned control, cells use these things called inhibitors.
Think of them like the brake pedal for an enzyme. They are molecules that bind to the enzyme to either slow it down or stop it completely. They are absolutely critical for keeping everything in balance. Okay, so the first type is called competitive inhibition, and the parking spot analogy is perfect here. Imagine an inhibitor molecule that looks so much like the real substrate that it could actually sneak into the active site and just park there. It physically blocks the real substrate from getting in.
Then you've got non-competitive inhibition, which is a little sneakier. In this case, the inhibitor doesn't even go for the active site. Nope, it binds to a totally different spot on the enzyme. But when it does that, it causes the entire enzyme to change its shape, and that change warps the active site so that the real substrate just can't fit anymore. It's a really clever way to shut the whole operation down.
So let's put it all together. If enzymes are the accelerators of life and inhibitors are the brakes, you have this incredible, dynamic system of control. And that balance is what makes life possible. So it leaves us with this really cool question. As we get better and better at understanding and even designing these molecules, what happens when we can truly control them both? What becomes possible when we hold the keys to the speed of life itself?